Welcome to Unit 3, Lesson 1, Changes of State. By the end of this lesson, you should be able to demonstrate an understanding of the states of matter and changes of states, and identify the heating and cooling graphs. You'll know you've been successful when you're able to describe in detail the various terms, states of matter and changes of states, and you're able to demonstrate an understanding of the difference between heating and cooling graphs, and you're able to apply your learning to daily life problems. So water and all other forms of matter can exist in different physical states or phases: solid, liquid, gas, and plasma. So in a solid, the molecule that makes up a solid are arranged in regular repeating patterns. They are held firmly in place but can vibrate within a very limited area. Liquid, the molecules that make up a liquid flow easily around one another. They are kept from flying apart by attractive forces between them, and liquids assume the shape of their containers. Gas, the molecules that make up a gas, fly in all directions at great speeds. They are so far apart that the attractive forces between them are insignificant. Plasma, at the very high temperatures of stars, atoms lose their electrons. The mixtures of electrons and nuclei that result in the plasma states of matter. Changes of state. When solids, liquids, and gases absorb or release enough thermal energy, they change state. Solid can change into liquid, and liquid can change into gas. When a substance absorbs thermal energy, the particles of the substance begin to move faster and further apart. So as they absorb energy, a solid can turn into a liquid, which can turn into a gas. And as they release thermal energy, a gas can turn into a liquid, can turn into a solid. A change of state requires a change in the thermal energy of the substance. So if we consider what happens to a sample of ice, initially at -10 degrees Celsius, when it is continuously heated. So first, the ice warms up. Second, as the ice reaches its melting point of 0 degrees Celsius, it begins to change into a liquid because of the absorption of the thermal energy in the form of heat. The third, as the ice-liquid-water mixture is continuously heated, it continues to absorb thermal energy but stays at a temperature of 0 degrees Celsius until the ice has completely melted. In the fourth, the liquid water continues to absorb thermal energy until its temperature reaches its boiling point of 100 degrees Celsius. At this point, enough thermal energy has been absorbed for it to begin to change into a gas, and in this case, it's water vapor. And the last, the temperature remains at 100 degrees Celsius until all of the liquid has changed to water vapor. So we can model these situations on what is known as a heating graph or a cooling graph. I'm going to show you an image of each. So a heating graph is a graph that shows the temperature changes that occur while thermal energy is absorbed by a substance. And a cooling graph is a graph that shows the temperature changes that occur when thermal energy is being removed from a substance. In both graphs, the vertical axis, the y-axis, represents temperature, and the horizontal or x-axis represents the amount of thermal energy absorbed or released. So this is an example of a heating graph. So on the heating graph, thermal energy is being absorbed by the water molecules throughout the heating process. Temperature changes are occurring only when one state is present. So it has to be fully ice before it turns into liquid, completely liquid before it turns into water vapor. So we can't have ice turning into water vapor. It has to be completely liquefied before it can be turned into a gas. The temperature remains constant during a change of state because thermal energy is being used to change the potential energy of the substance's particles and not their kinetic energy. On the heating graph, this occurs when a solid is changing into a liquid and when a liquid is changing into a gas. The heating graph shows a distinct melting point and boiling point. Okay. And then if we look at the cooling graph, thermal energy is being released by the water molecules throughout the cooling process. Again, the temperature remains constant during a change of state because the thermal energy is being used to change the potential energy of the substance's particles. And this occurs on the cooling graph when a gas is changed into a liquid and when a liquid is changing into a solid. This is represented by the flat part on both graphs. In general, melting and freezing occurs at the same temperature, and boiling and condensation occur at the same temperature. So our melting and freezing points on the cooling graph are 0 degrees. Don't forget that during melting and boiling, thermal energy must be absorbed by the particles of a substance. This absorbed energy is needed to break the bonds that hold the particles together. However, during condensation and freezing, thermal energy must be released by the particles of a substance. The released energy now allows the particles to move closer together and become more organized. In each of these situations, the change in thermal energy of the substance results in a change in potential energy of the particles. In other words, when a substance melts, boils, condenses, or freezes, the absorbed or released thermal energy is being transformed into potential energy rather than kinetic energy. Since the kinetic energy of the particles does not change, the temperature of the substance remains constant during a change of state. So furthermore, the angled parts of each graph indicate a change in temperature and occur when only one state is present. The flat parts occur when there is more than one state present, and the flat parts indicate a constant temperature because one state is changing into another. The temperature remains constant during a change of state because thermal energy is being used to change the potential energy of the substance's particles. Okay, we talked about how on the heating graph this occurs when a solid is changing into a liquid and when a liquid is changing into a gas. And on the cooling graph, this occurs when a gas is changing into a liquid and when a liquid is changing into a solid. Again, these are represented by the flat parts on both graphs. Furthermore, we talked about how on the heating graph, thermal energy is being absorbed by the water molecules throughout the heating process. And on the cooling graph, the thermal energy is being released by the water molecules throughout the cooling process. The heating graph shows a distinct melting point and boiling point. The cooling graph shows a distinct condensation point and freezing point. The melting and freezing points are both 0 degrees Celsius, and the boiling and condensation points are both 100 degrees Celsius. In general, melting and freezing occur at the same temperature, and boiling and condensation occur at the same temperature. So, most solids sink in their respective liquids. Water is different. Ice floats on water because water is one of the few substances where solid is less dense than its liquid. This is based on the water molecule's chemical structure. Water molecules are V-shaped and have 2 hydrogen atoms attached to 1 oxygen atom. So they tend to look like this, of oxygen and hydrogen, which hopefully you've seen before. So as temperatures above 4 degrees Celsius, water molecules are relatively disorganized. As the temperature of water decreases, the molecules move more slowly, forming a more organized structure, so that molecules of ice take up more space than those of liquid water, which is why your ice cubes float in your drink. This is also necessary for nature because think of ponds and rivers that freeze over in the winter. The top layers are frozen, but the bottom layers are actually not. It's actually water, which allows fish and other water life to continue to live throughout winter. If it froze from the bottom up, all of the wildlife that lives in a pond or river or ocean would end up dying because there would be no space left for them. This is the end of our lesson, so be sure to complete the quiz below the lesson. And as always, if you have any questions, please be sure to reach out to your teacher.